window to the dark universe. This is your turn, Professor Masood.
Yes.
If you
Professor
share your
Scully.
screen, we will be happy.
Okay, so
yes, we see your screen. You can continue.
okay, so it should be only the screen, right? Am I right?
Everything is okay.
Everything's
You
okay.
can present
you can
your
hear?
talk.
Okay, fine.
Yes,
So,
yes, we see everything. You and
Professor
your
Scully.
presentation.
Thank you so much, Professor Scully, and very good evening from China. So I also would like to thank the organizing committee, especially Professor Benam and other team members for making these efforts very fruitful. So I hope this plan and this makes progress by leaps and bounds. So I'm Syed Masood, and I'm presently working as a postdoctoral researcher at Zhejiang University in Hangzhou. And previously, I'd been here a PhD student. And the topic I would like to present is actually related to some kind of terrestrial settings using quantum optical techniques and Casimir physics to understand the mysterious dark stuff in the universe. What I mean by dark universe is actually the dark matter and the dark energy. So it's based on very recent papers with my doctoral supervisor, Professor Wang Ligang, and other team members here. So one of them is published last year. It was in PRD, and also second one in PRD. So the first one deals with the dark energy, and the second one with dark matter. So a big background. So the outline is like this. I will first introduce and background to the field, and then I will talk about the dark energy and its non-thermal signatures via acceleration radiation. And the third one will be about the dark matter via acceleration radiation. And then I would summarize. So this is the present status quo of physics, as we know, all the way going back from classical physics to general relativity via Newtonian gravity on one side. So this is the cosmological side of the story. And then we have the short distance physics, that's the quantum mechanical side, leading all the way to quantum field theory, and then possibly a theory of quantum gravity. But unfortunately, we don't have a firm picture of quantum gravity, because how a quantum metric would look like, we don't have a firm picture about that. We have lots of theories, and I think most of us are familiar about this crisis. But nevertheless, we have a pragmatic approach due to many big people in the field, especially Stephen Hawking and others. So this pragmatic field we call as quantum field theory in curved space-time. So it is essentially the regime I'm talking about right now. It's a very pragmatic approach where matter is treated on the quantum footings and the black holes or the geometry in the classical sense. So one of the pioneering results in this field is, of course, by Stephen Hawking and Bill Unruh. It's about how particles are generated in curved space-time. So that will be related to the black holes and the Hawking radiation. And at the same time, if we have a non-inertial observer in an accelerated frame of reference, he will also see a kind of thermal particle generation within a flat Minkowski space-time. So this essentially describes the scenario in the mathematical terminology. So this is a Klein-Gordon equation with the operator algebra, and this is the interaction Hamiltonian between the field phi x and sigma plus minus is the internal structure of the detector, so-called Unruh-DeWitt detector, and then this xi is a switching function. It's a function of proper time, and then g is the atom field coupling coefficient. And normally, this thing which I call vacuum thermality here is essentially the fact we use in normal quantum mechanics and harmonic oscillators, for example. When we take the expectation value of the number operator, it usually comes to be 0 in ordinary quantum mechanics. But when we go to non-inertial frames, this more holds true, and we have a non-zero value for the particles, even in presence of vacuum, real particles I'm talking about, and that's something that leads to Hawking radiation or Unruh effect. So for example, here you can see a trajectory, an accelerated trajectory from the perspective of a lab observer. So this trajectory is a so-called Rinder trajectory. It determines an observer who is moving through a flat Minkowski space-time, and within this Minkowski vacuum, he just sees a thermal generation of particles behind him, and that the temperature of this radiation is proportional to its proper acceleration. This is something that William Unruh discovered. So essentially, they are same. We have actually from Hawking's, we have from black holes, we have the Hawking radiation, where the surface gravity kappa plays the role of this acceleration, which is actually in the flat space-time. So essentially, they are same. There's a there's a sense, the sense of the radiation that's generated is a Planckian in nature. So, but whether it's really Planckian in nature, I mean, the particle spectra is believed generally to be Planckian. Well, whether this condition truly holds is still debated in the field. And I would like to cite one of the prime examples where this ideal spectrum, I mean, this ideal Planckian nature would break down, which
Professor
lovely.
Masood,
Yes.
we can't see your other slides rather than the first one. We only see your first page. Maybe you need to make a reshare.
Okay, so let me stop and start again. Okay.
Okay. Sorry for this flow.
It's okay. I think now it should be visible.
Yes, introduction and background. That's the title of your slide. Yes. No. Okay,
now
continue.
should be, right?
Yes, it's Hawking Unruh effect one.
Yeah. Okay. So the moment is it going here and there?
Yes, now the shifts are visible. Thank you.
Okay. Thank you so much for letting me know. So I was talking about actually what happens to an observer who is actually accelerating within the flat Minkowski spacetime. So within this region, where we define a perfect vacuum normally using the quantum field theoretic approach and Lorentz symmetry, so we have a thermal generation of particles, and the radiation that's thus generated has a certain characteristic temperature, which is called Unruh temperature, and it's proportional to the accelerating observer's proper acceleration. And what I wanted to say here was that the Hawking's and the Unruh's effect is essentially same. So they have the same Planckian factor, which determines that the nature of the particle creation is, in general, it's Planckian in nature. But whether this Planckianity or the Planckian nature of this radiation emission is always a Planckian thermal, it's indeed debatable. And one of the prime examples where this breaks down, this condition essentially breaks down. There's a lovely paper by Parekh and Wilczek in which they showed how Hawking radiation can be envisioned in some sort of tunneling from the black holes, which is very famous actually, Hawking's the tunneling approach to Hawking radiation, in which they showed that the back reaction from the geometry can break the Planckian thermality of the spectrum. So we will have a non-thermal spectrum in general. And there are certain nuances about this thermality and non-thermality. I would like to refer for the interested audience to a very lovely article by Matt Visser in 2015 JHEP. So these are some of the basics about this Hawking-Unruh effect. I go deep down now and talk about the possibility of observing these exotic things actually within the lab settings. So we know that Hawking's and Unruh's effect, they are very subtle phenomena. They happen in a vacuum. They happen in complicated geometries or spacetimes or accelerated frames. Whether we have the method to understand them using the non-terrestrial techniques is really it's $1 million question actually. But happily, over the last couple of decades, a lot of progress has been made in which we have been able to simulate or mimic these exotic systems within quantum matter and these quantum optical settings. So I just refer to the references here actually, which talk about dielectric media and then the quantum matter systems, quantum simulation using these Bose-Einstein condensates and etc. And also very important effect beyond Hawking-Unruh effect is the Parker's particle creation in curved space-time. This is essentially the same. I mean, they share the same underlying principle. I go further deep down the rabbit hole, and I want to talk about whether it's possible that we can use quantum optics to understand the Hawking-Unruh effect. So this is essentially what I would be moving around. Very recently, there has been a very nice attempt by a group led by Merlin Scully and others, and the subsequent works in this direction. There are a lot of papers in this direction. A particular radiation that comes about when the neutral atoms fall freely inside a black hole. This is a Schwarzschild black hole here, and the atoms fall down freely. But what's different here in this scenario is that this black hole is surrounded by a mirror or a Casimir-type boundary, which actually shields the possible incoming Hawking flux from the black hole. So essentially, we are using this black hole as a source of acceleration, and then within this setting, when the atoms fall down, an observer who is at the distant point from the black hole's center will see some radiation coming from the atom at the cost of the acceleration. That's because of the accelerated boundary, this Casimir boundary, which is here. So they observed that this particular radiation has certain characteristics that resemble the Hawking's radiation, but there are certain characteristics that are entirely different from the Hawking radiation. So it automatically finds connections to the accelerated boundaries, which of course we know the fluctuating boundaries or the accelerated boundaries refer to the Casimir plates. So it's essentially a dynamical Casimir effect in the black holes, and also connected to the conformal symmetry of the black hole. And it's known to be thermal for all asymptotically flat spacetimes, including the anti-detector space. So there is also a particular entropy area relation for this particular radiation. So they have called it as horizon Brightfield acceleration radiation, and it essentially comes from these virtual transitions happening in the cavity, atom cavity settings. So something that's very different about this is that when we have black hole in such a setting that a distant observer is defining the field around the black hole, he essentially defines the vacuum state as to be the Boulware vacuum state. And with respect to this distant observer, normally there is no Hawking radiation coming from the black hole. And in order to make sure there's no flux coming from the black hole, we shroud it entirely with this Casimir boundary. So it serves two purposes. One, it provides the acceleration to the atom, not actually the atom, the field that's around it. And second, it shields from any Hawking quanta, though whatever is coming from the atom actually comes from the vacuum transitions, actually virtual transitions. So this particular radiation has a lot of characteristics different from Hawking radiation. For example, they have also shown there's a phase correlation between the quanta. So essentially, it's not like Hawking correlated. There's a lot of things actually the Hawking radiation. So it's essentially different there. So now I want to show a contrary example where we can show that there is a possibility that the radiation spectrum associated with this particular phenomena could be non-thermal in nature. And then the question is actually whether we can understand dark energy and dark matter by means of these atom field dynamics or these Casimir physics. So first, it's a well-known fact that the total energy budget of the universe around is almost 70% comprised of dark energy, and 27 is the dark matter, and rest is the baryonic matter. So dark energy is a very big component as of our current understanding as it goes. So this is what we consider here is an Einstein gravity coupled to a positive cosmological constant. So this is essentially a de Sitter black hole. And one of the earliest attempts to understand the nature of radiation emission from this was, of course, by great Stephen Hawking and Gary Gibbons, in which they just showed that there are existence of two horizons for this black hole. One would be the event horizon, which is RG, and another would be R lambda. That would be the cosmological horizon. So these two horizons actually give rise to two types of radiations, one coming from the black hole side, another coming from the cosmological side. It's a bifurcate filling horizon, so things are very complicated here, especially the mathematics also goes very complicated. So this is actually the Rigger-Wheeler, the tortoise coordinate, which is very handy in handling the field propagation in curved spacetimes. So this is actually, the positive lambda has been a subject of intense investigation when it comes to the thermal generation or the non-thermal generation of particles. We're using the same method here. We are using the same space-time geometry here and want to understand what really happens to the neutral atom actually when it falls down the black hole. So I'm showing here a black hole which is shaded in black, and then there is this Casimir boundary that sits around above the black hole's horizon. It's just hovering the horizon of the black hole, and the atom falls down from this point and goes to the horizon. So it falls against this Casimir boundary. And then this boundary, the blue region, the boundary of the blue region is exactly the regime where the cosmological forces due to gravity and the dark energy balance each other. We know that cos 2 lambda creates anti-gravity effect. So essentially, if we go asymptotically de Sitter, it will be pulling everything away, and close to the black hole, it will be pulling towards the black hole. So essentially, there should be a kind of neutral point where the forces balance each other. So this is our starting point of investigation. We do not worry about the rest of the things. So what we are concerned about is the motion of the atom, which falls down, and this motion carries with it, which I climb here, carries with it the signatures of positive cosmological constant. And we want to see what happens to the radiation that this atom emits. So observers should be somewhere here actually, and we have to take a lot of approximations later on that will be clear. So when this happens, we want to see what's happening to the black hole, this radiation emission, when we have the presence of positive lambda. If there was no lambda, we would have a flat space and there was no problem in defining vacuum states and all that. So the observer would have been at infinity in principle, but here we are compelled to put the observer in between the horizons, and he's making the measurements and measuring the spectrum that is emanating from this falling atom. So these are the mathematics and the geodesic trajectories for the atom. It's falling down. And finally, what we want to compute here is the coordinate and conformal time. But since in the denominator, we have a lot of complications due to the space-time horizon, the horizon structure of the space-time. Generally, it's not possible, and there are a lot of efforts have been paid in this direction. But we introduced here very simple methods to compute this approximately. We can see here this epsilon square is usually the specific energy of any object that's falling down in the black hole. So it's usually related to the maximum of the metric function of the black hole. Metric function has the maximum here at the neutral point between the two horizons. So whenever we have epsilon square greater than f of r, we can make an approximation that we can expand the denominator, and we are green with calculating this conformal and coordinate time. We can see here I have expanded, and we have gotten this coordinate and conformal time for this particle, and we can see here a typical gravitational time dilation is displayed here by the atom. And only I want to point out here is actually what's the impact of lambda here. We can see here if we put lambda's least value, which is blue color 10⁻⁵. You can see here it has the maximum value compared to the red color, which corresponds to 10⁻². Essentially, what's happening here actually, if the atom starts its journey here somewhere at a finite distance from the black hole, goes to the event horizon of the black hole, and from the distant observer's point of view, which actually measures the coordinate time, to him actually atom will never really cross the horizon. And this is actually true for the Schwarzschild black hole as well. Well, what's truly different here is actually the role played by the lambda. So what's happening here actually, as we go on increasing lambda, there will be a decrease in the coordinate time at the horizon. The reason being very simple: positive lambda will inflate the black hole, and this will essentially take less time for the atom to reach this black hole's event horizon. And same is the case for conformal time, which normally is the case, which is the time measured by the atom's own clock, and it will always cross in a finite time. So, but here, what lambda is doing, it's inflating the black hole, so the atom will cross the horizon very quickly compared to the one where we have no lambda. So lambda has the inflating character to the black hole. Now we come to the quantum, the wave equation side. We solve the Klein-Gordon wave equation. And then we put the wave equation in terms of t and r star coordinates, and we make a lot of approximations here, which we have to be very careful about. If we ignore any potential here that usually generates the scattering effects in the curved space-time, we are completely ignoring it, and we can ignore it by taking the approximation that the frequency of the emitter radiation very, very, very high. It's highly energetic wave, and it can leave the horizon of the black hole, and it can perfectly reach the distant observer, because we are essentially talking about what's the nature of this radiation. We're not talking about the scattering effect. But of course, if we take the scattering effect, it's altogether a different scenario. And also the geometry between these two horizons, this neutral point, should be very wide region, which is possible by taking very small value of lambda. And when this is a very wide region, we can essentially treat it as a Minkowski region, and it will be very far away from the black hole, and we can define a Boulware vacuum state for that very easily. That's not a problem. So the observer should not be close to either of the horizons. When we take these approximations, we have a simple plane wave mode, and which can also be taken care of by cavity adjustments. We have a single plane wave with frequency nu of the radiation, and then we have this wave mode that's emitted by the atom. This is actually the interaction Hamiltonian between the atom and the field. So this is the internal structure of the atom, sigma tau. And then we have this psi n, tau, t, and r, which is actually the radiation part of the spectrum. And g is the atom coupling constant, h cross is this Planck's constant. So we can use time-dependent perturbation theory. And finally, coming to the final equations, we can put everything in terms of radial coordinate. Atom falls down from the distance. We should be R0 in principle to the RG event horizon of the black hole, but we cannot use R0 exactly because we have taken that approximation to define coordinate time and conformal time. So we take minus delta, where delta is the deviation from the limit point. So when we take this, we use numerical approximations, and we want to see what's the behavior. Originally, if we go to the edge bar radiation, we have seen that we have the freedom to choose this limit. Upper limit could be infinity, and the lower limit could be event horizon. By the certain transformations, we can put it in a kind of a form that leads to the thermal generation. But here we have certain problems because of the bifurcate killing horizons. So this is the particle, the particle creation profile because of the dark energy black hole, the de Sitter black hole. So essentially, at first sight, what we see here is that atom will emit and its emission would be dependent on the value of lambda. The least lambda would have the least amplitude, and the largest value of lambda will have the largest amplitude. This is one of the observations. We also provide a heuristic explanation for this. But for things to be seen, when we remove lambda, in order to juxtapose these things, this should be a pure Schwarzschild black hole, and this is a de Sitter black hole. When we have this scenario, actually, we can see here, we have a kind of Bose-Einstein spectrum, which should be for this Schwarzschild black hole, and we will later on see when we can retrieve this actually. So here, what is happening actually, whenever we increase the lambda, it increases the intensity of the radiation. And also, at the same time, we can see here when we increase the atom's transition frequency, which actually determines that whether we can easily excite the atom or not, we can see here it becomes difficult to excite the atom. So it becomes the impact of this radiation on this the impact of the atomic transition frequency on this radiation spectrum is that this is the lone criteria by which we can normalize the radiation actually. So because we have the only factor omega actually that determines this. And then we can also see here that delta, which I talked about, if we are keeping it very small, we can see the radiation profiles will almost merge with each other. So, and if we make it very bigger, we can see they deviate from each other. So we have to take the limiting value. It should be as small as possible. Now, I will only provide the explanation for this case. Why does it increase the particle creation profile? It's just an intuitive picture. I'm not saying it's an exact picture, just an intuitive physical picture. So we know that tidal forces really weaken the Hawking radiation and because of the back reaction effects in the space-time. And it's also linked to the surface gravity of the black hole, which is related inversely to the size of the black hole. Because the dark energy makes the black hole big size, that means the tidal forces are really reduced. So maybe this is the reason that we see the enhanced spectrum for the particles here. So because the gravity becomes weaker because of the dark energy. But exactly what's happening here, we don't have this kind of spectrum, which would have been a Bose-Einstein spectrum. And that means the thermal generation, which was reported for a pure Schwarzschild black hole, is broken down for all kinds of possible values of lambda. And we can do nothing here. This is an approximation which we have used here. To the best of our approximation, we have shown that this could only be the case that we cannot have this perfect generation of particles in the Bose-Einstein's way. And we can also retrieve the lambda zero limit, and we can see that it almost approached the Bose-Einstein spectrum that was reported earlier for most of the asymptotically flat black holes, which somehow lends confidence to what we have done here. And now I will jump to the dark matter sector. We know that the dark matter makes around 27%. There are a lot of models for the dark matter. And what we have taken care of here is actually a perfectly dark matter. So a perfectly dark matter has this kind of distribution. It has recently attained a significant attention in the field. So that's why I took this dark matter candidate. We can see here when we add dark matter to a black hole, essentially what it is doing when the density of the dark matter is increasing, it just decreases the black hole size. And then when it increases, then beyond this particular point, it will inflate the black hole just as the dark energy does. So what is essentially happening here is that there's a critical value for the dark matter density, and below which we have this decreasing black hole shrinks in size, and beyond that, the black hole inflates in size. I calculate the event horizon of the black hole, which was here, and then this is the scenario here. But only difference is that the dark matter density is closest to the black hole horizon. As we gradually move far away in the R infinity limit, the dark matter density goes to zero, and we recover the Minkowski spacetime. And for that, we have a freedom to choose the settings, and we can define a Boulware state very easily. And proceeding in a similar way, using all kinds of approximations, we can see here what dark matter is doing. It's essentially doing the same things as that of the dark energy, but for the part when it's greater than the critical density because the black hole inflates in size. For the rest, it's making black holes shrink, and accordingly, time coordinates change. So finally, we are led to this probability equation, which talks about the intensity distribution of radiation. So doing all these approximations and then these coordinate transformations, we are led to this equation, which we can numerically compute. And we can see here, there's a thermal generation of particles here when we have alpha less than alpha, and we have alpha greater than alpha. And we change alpha from 0 to 0.5 for the choice of mass of the black hole, m being 1. So what essentially is doing here, as we increase the particle density, the dark matter density, it's reducing the particle intensity profile. And as we go beyond the critical density, energy, it's increasing, enhancing the particle distribution. And at the same time, if we see what's the impact of lambda here, so it's essentially reducing this particle intensity here because of the energy conservation reasons. Because if we have an atom that has a large transition frequency, it's very hard to excite the atom. So we would have few particles of that energy. And at the same time, to see what mass is doing to the black hole, it's somehow playing the similar character to that of dark energy, because it's kind of enhancing the particle spectrum here. To see this more closely, we have plotted this probability distribution against the mass of the black hole. We can see here it monotonically increases the particle spectrum profile, this H-bar radiation. And that means for the supermassive black holes, this should be very prominent actually. This is a conjecture from our side. And to see whether this flux is this finite at the origin or infinite at the origin, because the Bose-Einstein spectrum profile should be very clear. We can see it's very finite at the origin, and it goes to zero and decays to the zero when we go asymptotically in the far end of the spectrum of the radiation. So I would summarize here. What I talked about was a particular radiation that emanates from Casimir settings, where we have the atom going through the cavity in the black hole. That black hole is actually surrounded by dark energy and dark matter. We saw that dark energy has the capability to enhance the particle spectrum. It can break the particle nature, this Planckian thermality of the particle spectrum. And then we can also see that when we have the dark matter, the perfectly dark matter candidate here, it can degrade the spectrum of the particle. It can enhance the particle spectrum depending upon whether its value is beyond a certain critical density or below the critical density. And we also see that black hole mass will somehow have the same effects, the geometric effects, as the dark energy. And this effect should be more pronounced for the supermassive black holes here. So what we showed actually, it's indeed, if we go deep down to understand, this is actually a thought experiment as of now. I would not say this is a perfect Casimir apparatus. So it's a thought experiment which somehow helps us to understand what's the really nature of these mysterious dark stuff when we want to understand it from the non-terrestrial techniques from quantum optics or the Casimir physics. So I leave it there. Thank you so much for being so patient. Thank you so much again to Professor Scully and then Professor Benham and the organizing committee and the respected audience. Thank you so much. So I will leave you there. And I'll be most happy to talk about this. If you have any questions, I'll be most happy to answer.
Dear Professor Masood, thank you very much for this very interesting and very comprehensive talk. Do you have any questions? And this is for our participants. Actually, I have one and I shared in the chat board, but let's take the others' questions first. Then we can pass to Mayan's question.
Sure. Thank you.
Any questions? Actually, when I listen to your talk, I remember the Gedanken experiment of Bekenstein. The Bekenstein, while he prepared his paper about the quantization of black holes, they made such a scenario how a black hole absorbs the matter and how the area will be quantized because of that absorbing. Somehow this is your scenario, something like that. But it is really good work. I congratulate you. But if you read my question in the chat board, I am wondering, can you see my question?
Let me go to the screen. So I will stop the screen, then I can see. Okay. I think.
Okay.
Maybe, yeah, I can see the chat and yeah, my question 1. Okay,
yes.
So.
And there's a picture about there. It's related with the entropy area relation. And I don't know whether you have worked on the information paradox before and how your work will affect the information loss paradox question, because I'm sure that they are really related issues and it may be a recipe for this question, long-standing question as well.
Yeah, so on this, I would remark like this. So for this particular radiation that emanates from the atom cavity apparatus, they have successfully shown, even in the first paper and the subsequent papers, that there is a kind of phase correlation between the quanta that are emitted from the black hole, this particular radiation. So when we have the phase correlation between the quanta that are emitted from the black hole, essentially this does not normally lead to the information paradox. They have some remarks in the paper about this.
Oh, very good. So I will read it.
Yeah. Yes, yeah, it's very
Professor
nice.
Professor Fabiano Santos is a question. Please unmute.
Thanks, Isaac. And congratulations for the best talk. It's very
Well,
powerful. I have a question, but I think that in some sense you answered this question. But what happened when you is extending this model for the modified gravity theories? Because you change the Beckstein-Hawking entropy in these theories.
right.
This description excluded these theories or not? Or it's possible you have some modifications on your physics, or it's not possible?
So are you, sorry if I misunderstood, are you talking about the Bekenstein-Hawking area entropy relation within modified gravity paradigm?
Yes, for this,
For
it's
this
possible to
particular
have this in this effect?
You mean for this particular scenario?
Yes.
Actually, the follow-up works, there are certain, let me answer it like this. To my observation, actually, most of the modified gravity theories, I would give a very general remark and come exactly to this point. Most of the modified gravity theories, beyond Einstein gravity, actually, most of the theories predict something that help us to understand quantitatively and phenomenologically what's different between Einstein gravity and those theories. And essentially, one of the attributes or one of the parameters to quantify this is to see what's happening to the event horizon of the black hole, right? So I would say that if we have modified gravity theories, they have a different event horizon than compared to the Einstein, four-dimensional Einstein gravity, right? So I have seen many papers in this particular context which talk about the modified, not to say the modified gravity, but at least the gravity which has quantum corrections. For example, we have the quantum modified Schwarzschild metric. So only what they have done is like they have actually calculated the quantum corrections to this Bekenstein-Hawking entropy area relation for this particular radiation type. So the quantum nature of geometry is again manifesting through this particular radiation. So just as quantum corrections, yeah. So I would conjecture here, maybe the modified gravity theories, which also kind of contribute to the Bekenstein-Hawking paradox, Bekenstein-Hawking entropy relation, they should manifest in some kind of higher order corrections to this Bekenstein-Hawking, this entropy area relation, yeah.
Okay, thanks. Because I am working on the modified gravity theories to study the black hole information through the entropy and the transport coefficient for the many scenarios of the condensate matter and strongly coupling system. And this is very interesting because few years ago, I am trying to study the Casimir effect in the modified gravity theories, but I am stopped because here I am changing for the another institutions because I think that all guys here have the same situation in some sense, and I am stopped at this, right? But when I see you're talking the list of the participants, I see I study your this point, and I think, oh, okay, it's a good opportunity for me asking a question about this. Is have the work in some sense. But thanks a lot for your answer. And thanks a lot again for your nice talk.
Thank you so much. Thank you so much. Really humble, really kind of you.
Any questions? Yes, Professor Masood. We really thank you for this great talk, and hope to see you again in the upcoming and then conferences. We will follow you because you are doing really good jobs. Congratulations and thank you very much.
Thank you very much for the chance. Thank you.
Okay, the next speaker will be Professor Loris Krauss. However,